We're going to continue our discussion on stoichiometry in sections 4 and 7 of chapter 5. First, we need to demonstrate the concept of the mole by using Avogadro's number to calculate numbers of atoms or moles from numbers of atoms. The mole is a unit of counting, and it has a value equal to 6.02 times 10 to the 23rd items. The units on that number, Avogadro's number, symbolized with a capital N sub capital A, is interesting. The units are inverse moles. Moles to the minus 1. That means that you can put anything on the numerator that you want. So you can have 6.02 times 10 to the 23rd atoms per mole. 6.02 times 10 to the 23rd molecules per mole. 6.02 times 10 to the 23rd chickens per mole. Now, it is only through the use of the mole that we can count our particles within a substance through weight. So here we have a series of substances. Copper. 1 mole of copper has a mass of 63.55 grams, and it contains 6.02 times 10 to the 23rd atoms. Similarly, aluminum contains 6.02 times 10 to the 23rd atoms, but its weight is 26.98. It is less massive. It has less protons and less neutrons. Therefore, the mass should be lower. But the number of particles is the same in both cases. Similarly, for iron or mercury, they all contain the same number of particles, 6.02 times 10 to the 23rd, even though they have different masses, 55.85 and 200.6 grams. We can use Avogadro's number as a conversion factor in calculations. So, for example, let's start off with the first problem here. 0.224 moles of water. And to fill in the table, we want to find the number of molecules in a sample. So how many molecules are in 0.224 moles of water? So, following dimensional analysis, we want to make sure that moles is on the bottom. And since Avogadro's number has the unit of per mole, that means the 6.02 times 10 to the 23rd molecules of water is on the top. And when we do that multiplication, we get 1.35 times 10 to the 23rd molecules of water. First thing I want to point out is before, when we had numbers and doing dimensional analysis, we only talked about the unit, making sure that we had our correct units. When we start stoichiometry, we want to make sure that we also include materials we are working with. So in this case, we had water. The reason we want to continue making sure that we know what the material is that as we go through stoichiometry, we're going to often be changing from one material to another material through the use of chemical equations. Therefore, it's very important that you keep track of the material you are using. Now let's move to the next total atoms in the sample. So if I've got 1.35 times 10 to the 23rd molecules of water, now I want to find the total number of atoms. So in one molecule, I need to have molecules cancel. One molecule of water, how many atoms are present? Well, we've got 2 hydrogen and 1 oxygen. So a total number of 3 atoms present. And when we determine the math on that, we get 4.05 times 10 to the 23rd atoms. Let's do the next problem. 2.71 times 10 to the 22nd molecules of CO2. And let's turn that into moles. So 2.71 times 10 to the 22nd molecules of CO2. We want to turn that into moles, so mole needs to go on top. 1 mole, and then Avogadro's number will be on the bottom. 6.02 times 10 to the 23rd molecules of CO2 for every 1 mole of CO2. And when we do the math on this, we get 0.0450 moles of CO2. One of the common misconceptions that students often have is when we have numbers like 0.0450 moles, they don't quite grasp how that can actually be a count. And it's actually pretty simple. We use the concept of the mole and the concept of the dozen very often interchangeably to show you that it's just a unit of counting. So if you have 1 dozen donuts, you have 12 donuts. If you have 1/2 of a dozen, you have 6. If you have 1/4 of a dozen, you have 3 donuts. But what would 0.1 of a dozen be? That would be 1.2 donuts? That doesn't make sense because you can't count a 0.2 donuts. What's 0.2? So this is different because 12 is such a small number compared to Avogadro's number. Avogadro's number is incredibly huge. 6.02 times 10 to the 23rd is just a really, really big number. So you can have very small fractions of that number and still have a large number of whole atoms that you're counting. In section 5, we're going to talk about calculating molar masses of a substance and using molar mass to calculate moles from mass and vice versa, and utilize both molar mass and Avogadro's number to calculate number of particles from mass and vice versa. The concept of molar mass is an interesting one. We have, by definition, stated that 1 mole of isotopically pure carbon-12 has a mass of exactly 12.00 grams. By stating that this isotopically pure carbon-12 has a mass of exactly 12 grams, what we're doing is we're putting all of the numbers that are on the periodic table into masses that we can actually weigh in the lab. So we're looking at lab quantities, grams per mole. All the periodic table masses then can be thought of as grams per mole. Before they were AMUs. When we talked about average atomic masses, we did them in AMUs. However, if we're looking for something in the lab, something that's large quantities that we can see, we're talking about gram quantities, not atomic mass units. AMUs are useful when we have single atoms or single molecules. They're not as useful when we try to talk about chemical reactions. That is where we use the grams per mole. We have 3 different calculations of mass that we're going to talk about. We have the molecular mass, which is the sum of masses of an element in a compound, and that is in AMUs. Okay, that's only molecular compounds, so nonmetal to nonmetal. Formula masses are the sum of elements in an ionic compound. Okay, so these are the units of AMU as well, since these are the sums of individual ions in the ionic compound. But the molar mass, this is the sum of the masses of all the elements in a compound. It doesn't matter whether it's ionic or molecular. It doesn't matter the type. The molar mass has units of grams per mole. Use AMUs when you're looking at single particles. Use grams per mole when you're talking lab quantities. Now, because they are exactly the same, the sum total of the masses of the elements in the compounds, often we use these words interchangeably, saying molecular mass when we really mean formula mass, or saying molar mass when we mean molecular mass, or vice versa. It doesn't matter. Pick the units you need. If you're looking at single atoms or molecules, AMUs. If you're looking at lab quantities, grams per mole. Let's do a molar mass calculation. Chloral hydrate C2H3Cl3O2 is a drug formerly used as a sedative and hypnotic. It is a compound used to make a Mickey Finn in detective stories. Calculate the molar mass of chloral hydrate. So, we've got the formula C2H3Cl3O2. To determine the molar mass, I'm going to use the periodic table, and I'm going to look at each of the atomic masses and add up the sum total of all of the masses present in the compound. From my periodic table, I see that carbon has a mass of 12.0107 grams per mole. Now, I've got 2 carbons, so I'm going to multiply that by 2. I've got 3 hydrogens, and my hydrogen is 1.00794 grams per mole, but I have 3 of those, so I'm going to multiply by 3. I've got 3 chlorine, and chlorine from my periodic table says 35.453 grams per mole, and multiply that number by 3. And then finally I've got 2 oxygen, and each oxygen is 15.9994 grams per mole times 2 of those guys. Doing the multiplications, I get these numbers here: 24.0214, 3.02382, 106.359, and 31.9988. When I take the sum of these guys, I get 165.40302 grams per mole. Now, that's way too many significant figures. So I need to go back and double check. Now, remember, the significant figures is really going to come from the addition. So I start off with carbon. I've got 1, 2, 3, 4, 5, 6 significant figures, and 4 decimal places. I've got 1, 2, 3, 4, 5, 6 significant figures in the hydrogen, but to 1, 2, 3, 4, 5 decimal places. I've got 1, 2, 3, 4, 5 significant figures, but to 3 decimal places, and 1, 2, 3, 4, 5, 6, but to 4 decimal places. So the sum total in my addition should end up with 3 digits after the decimal point. So my answer should be 165.403 grams per mole. Now, it's often questioned whether you have to write out all of the significant figures as given on the periodic table. And my suggestion is to do your molar mass calculation determinations such that you get at least one more significant figure than whatever is given in your problem. So if they give you a problem that has 3 significant figures, make sure you get at least 4 significant figures in your molar mass calculation. If you're given 5 sig figs, try to get 6 for your molar mass calculation. So try to always get one more significant digit greater than what is your given. That will help you to avoid rounding errors. Now let's do a problem where we use molar mass as a conversion factor between mass and moles. So how many moles of a sample do I have if I start with 4.24 grams of C6H6? So the first thing I need to do is I need to find the molar mass of C6H6. So I have 3 significant figures in this, so I need to make sure that my molar mass has got 4 significant figures. So what I'm going to do is I'm going to do over to the side, I've got 6 carbons, that gives me 6 times 12.01, and I've got 6 hydrogens, so 6 times 1.01, and when I add these guys up, I get a total molar mass of 78.12 grams per mole. So I'm going to use that as a conversion factor. I want to find moles. 1 mole of C6H6 weighs 78.12 grams of C6H6. And we get 0.0543 moles of C6H6. Now, continuing this problem, if we want to find out the number of molecules in this sample, we would take the number of moles we were given, 0.0543 moles of C6H6, and we're going to convert it to molecules in the sample by Avogadro's number. So there's 6.02 times 10 to the 23rd molecules of C6H6 for every 1 mole of C6H6, and that gives us 3.27 times 10 to the 22nd molecules of C6H6. If we want to carry it further into total number of atoms, we would take the 3.27 times 10 to the 22nd molecules of C6H6, and how many atoms do we have per 1 molecule? there are 12 atoms, 6 carbon, 6 hydrogen, for every 1 molecule of C6H6. And that gives us 3.92 times 10 to the 23rd atoms. All right, let's tackle another problem. The molecular formula of acetylsalicylic acid, or aspirin, one of the most common used pain relievers, is C9H8O4. They want us to calculate the molar mass of aspirin, and then ask us a typical aspirin tablet contains 500 milligrams of C9H8O4. What amount in moles of acetylsalicylic acid molecules and what number of molecules are in a 500 milligram tablet? So, let's start off with what we know. We've got our formula is C9H8O4. So I've got 9 carbon atoms. That's 9 times 12.01. 8 hydrogen atoms. 8 times 1.01. And 4 oxygen atoms. And 4 times 15.999. For a sum total of 180.16 grams per mole for aspirin. That's part A. Now part B says a typical aspirin tablet contains 500 milligrams. What amount in moles and number of molecules is that? So, I know I've got 500 milligrams of acetylsalicylic aspirin, or aspirin. Sometimes we can abbreviate our formulas. If we don't necessarily need to have the formula all the time, sometimes we'll just give it a name, like aspirin, but with an H, telling me it's an acid, the acid of aspirin, times 1 gram is 1,000 milligrams. I need to get that into grams. And then I'm going to multiply by a conversion factor, which is my molar mass. So I want moles. So 1 mole of aspirin, HASP, is 180.16 grams of the HASP. That gives us the total number of moles, which is 2.78 times 10 to the negative 3 moles of HASP, or aspirin, or C9H8O4. So that's the first part. That's the number of moles. Okay. Now we want to find the number of molecules. So I'm going to take the number of moles, 2.78 times 10 to the minus 3 moles of HASP, aspirin, times 6.02 times 10 to the 23rd molecules is 1 mole of aspirin. And that yields us 1.67 times 10 to the 21st molecules of aspirin. In section 6, we're going to talk about calculating percent compositions by mass from formulas of a compound. Recall the laws of multiple proportions and constant composition refer to ratios of weights of elements and compounds. For example, we said that 1 gram of hydrogen and 8 grams of oxygen was always water. That if you had a compound that was not 1 gram of hydrogen and 8 grams of oxygen by mass, you didn't have water. We can use these percentages by weight to help us determine formula, and it's also very helpful sometimes to be able to determine the identity of something through its percent composition. This is best illustrated using a problem. In 1987, the first substance to act as a superconductor at a temperature above that of liquid nitrogen was discovered. The approximate formula of this substance is yttrium, barium-2, copper-3, oxygen-7. Calculate the percent composition by mass of this material. So what we're looking for is how much of the whole is yttrium, how much of the whole is barium, how much of the whole is copper, and how much of the whole is oxygen. So the first thing we need to do is we need to determine what the molar mass of the whole thing is. So here are all my masses of my elements and their composition. So we've got 88.906 yttrium, 137.327 times 2 for the barium, 63.546 times 3 for the copper, and 15.999 times 7 for the oxygen. This gives us a sum total mass of 666.191 grams per mole. Now, to determine the percentage, we're going to take each of the individual atomic masses over the whole. So the percent yttrium is equal to 88.906 over the whole, 666.191 times 100. The percent barium is going to equal that 2 times the 137.327, because we've got 2 of them, over the whole, 666.191 times 100. The percent copper is going to equal the 3 times the 63.546 over the sum total, 666.191 multiplied by 100. And then finally, the percent oxygen is equal to 7 times 15.999 over the 66.191 times 100. So completing the math, we end up with 13.345% yttrium, 41.2275% barium, 28.616% copper, and 16.811% oxygen. Now, a word about significant figures. Notice all of them have 5 significant figures except for barium. That's because barium, I was able to pull 6 significant figures out of that calculation, so my answer should contain 6 significant figures. Again, this depends upon which periodic table you use and the level of precision on that periodic table. If you have the ability to pull off as many significant figures as you can, feel free to do so. But do not round to the nearest ones place, okay? This requires some more precision than that. All right, in section 7, we're going to use mass percent data to actually calculate the empirical formula of a compound. We'll also be able to do that using data from combustion analysis, and we will calculate the molecular formula of a compound given the molar mass and empirical formula, or the data required to calculate the empirical formula. The empirical formula is the simplest whole number ratio of atoms in a compound. Okay, so the mass percent data that we get would actually give us the simplest whole number ratio. Since the meaning of the word percent means per 100, if we assume that we have a 100 grams of sample, then all of those percentages in the mass percent become masses. So once we get the masses, we turn each of those elements into moles. It is through ratioing the moles that we get the subscripts for our empirical formula. So the way we do that is we calculate all the moles out, find the smallest number of moles, and divide every single number by that number. Now, hopefully they are whole numbers. If they are not whole numbers, we sometimes have to multiply each number by an integer in order to ensure that we get whole numbers. So let's do a calculation for empirical formula from mass percent data. The most common form of nylons, which is nylon 6, is 63.68% carbon, 12.38% nitrogen, 9.80% hydrogen, and 14.14% oxygen. Let's calculate the empirical formula for nylon 6. So the first step is we assume we have 100 grams of sample. That means that each of those percentages now becomes grams. So 63.68 grams is carbon, 12.38 grams is nitrogen, 9.80 grams is hydrogen, and 14.14 grams is oxygen. Now we're going to convert each of these masses into moles using the molar mass of each of the elements. So 1 mole of carbon is 12.01 grams of carbon. 1 mole of nitrogen is 14.01 grams of nitrogen. 1 mole of hydrogen is 1.01 grams of hydrogen. And 1 mole of oxygen is 16.0 grams of oxygen. Now you'll notice I'm being a little bit fast and loose with the number of significant figures. That's because when we go to do our ratio, we're looking to get whole numbers. Sometimes it's better to be a little more generous on your molar masses than you would normally be. So let's do the calculations here. So when we do 63.68 grams of carbon divided by 12.01 grams, we get 5.302 moles of carbon. 12.38 divided by the 14.01 gives us 0.884 moles of nitrogen. The 9.80 divided by 1.01 gives us 9.70 moles of hydrogen. And 14.14 divided by the 16 gives us 0.884 moles of oxygen. So now we're going to look for the smallest number of moles and divide by that number. Well, we see that 0.884 is the smallest number, so I'm going to divide every single number here by 0.884. And when we do that, these guys are 1 and 1, and we get carbon being 5.99, which is approximately 6, and the hydrogen being 10.97, which is approximately 11. These are the subscripts for each of the individual elements. So our formula is C6N1, but we don't put the 1, H11O1, C6NH11O. That would be the empirical formula for nylon 6. How do we get mass percent data? Well, there's a bunch of different ways we can get mass percent data. There's also one other very common analysis tool that we use, especially with what we call hydrocarbons, things that contain carbon and hydrogen. When you burn hydrocarbons, they usually produce water and CO2. So, combustion analysis, we have a furnace. In the furnace, we place our sample, and we direct pure O2 into our apparatus, and we heat the sample up, and it burns. Now, this burns, giving off CO2 and water. We have a water scrubber made of magnesium perchlorate and a CO2 scrubber made of sodium hydroxide. So coming out the end is oxygen, and if there were any other molecules, they would also exit the end here. But the water has been absorbed by the magnesium perchlorate, and the CO2 has been absorbed by the sodium hydroxide. If I know the mass of the magnesium perchlorate before and after the experiment, then I can determine the mass of water absorbed. Similarly, if I know the mass of the sodium hydroxide before and after the experiment, I can determine the amount of CO2. Now, all of the carbon must have come from sample. And all of that carbon is now in the CO2. All of the hydrogen must come from the sample, and that's now in the water. So using this data, we can determine the amount of carbon present and the amount of hydrogen present, and we can use that data to actually reconstruct the empirical formula of our original sample. This is best illustrated using a problem. So we have a compound that contains only carbon, hydrogen, and nitrogen. Combustion of 35.0 milligrams of the compound produces 33.5 milligrams of CO2 and 41.1 milligrams of water. We want to know what is the empirical formula of the compound. So we know that there are only three elements: carbon, hydrogen, and nitrogen. We know that all of the carbon is now in the carbon dioxide. All of the hydrogen is now in the water. What about that nitrogen? That doesn't go anywhere except out the end. We have no idea what happened to it. But because it only contained carbon, hydrogen, and nitrogen, if I know how much carbon was in the original sample and how much hydrogen is in the original sample, and I know the mass of the original sample, I can determine the amount of nitrogen. So let's write down the rest of what we know. So the mass of the sample was 35.0 milligrams. We have the mass of the CO2 equaling 33.5 milligrams, and the mass of the water equaling 41.1 milligrams. Now you'll see that the mass of the CO2 plus the mass of the water does not equal the mass of the sample, and that's okay. That shouldn't be the case because we've got nitrogen as well, and we've got in the CO2 and the water, we've got extra oxygen. That extra oxygen came from the O2 we were pumping into the system. So the first step, we need to determine how much carbon is actually in the CO2. Now there are a few ways to determine the amount of carbon in the CO2 and the amount of hydrogen in the water. You could determine the mass percentage of hydrogen in water and the mass percentage of carbon and oxygen and multiply those two. Or you could do this. You could take the mass of the CO2, turn it into moles of CO2 using molar mass, which then we can turn into moles of carbon, which then we can turn into grams, mass of the carbon. Mass of the carbon, not grams, mass of carbon. So let's go ahead and do that. I've got 35.0 milligrams of CO2. Now, I'm going to use a little trick here. I am not a big fan of tricks, but you'll see that this is kind of a useful one. I'm going to turn the milligrams of carbon dioxide into moles using the molar mass. 1 mole of CO2 has a mass of 44.01 grams of CO2. How did I determine that? I took the oxygen masses and the carbon masses and added them up. Now, notice milligrams and grams don't cancel. But this is a neat trick. If I put a milli in front of the mole and a milli in front of the gram, now I have milligrams and millimoles. I didn't change the number because all I did was just scale down the size of it. As long as I do the same scale unit to both sides of the dividing line, it's fine. So now my milligrams actually cancels. Then I know that inside every 1 mole of CO2 there is 1 mole of carbon. Again, I can place that little milli in front. So now my millimoles cancel and I'm left with millimoles of carbon. And then finally, I want to turn that mass of carbon into grams or milligrams. So what I'm going to do is 1 mole of carbon weighs 12.01 grams of carbon, but if I put my millis in front there, I am left with the correct units. And I get that the sample contains 9.551 milligrams of carbon. I'm going to do the exact same thing with the hydrogen. I'm going to take the 41.1 milligrams of water, turn it into millimoles of water. There are 2 atoms of hydrogen, for every 1 molecule of water, so 2 millimoles of hydrogen for every 1 millimole of water, times 1.01 milligrams of hydrogen per millimole of hydrogen, and I get 4.610 milligrams of hydrogen. Now, why did I do that? I need to find out the mass of nitrogen. So the mass of the sample minus the mass of the carbon minus the mass of the hydrogen equals the mass of the nitrogen. So 35.0 milligrams minus 9.551 milligrams minus 4.610 milligrams gives me 20.8 milligrams of nitrogen. So now I've got the mass of the carbon, the mass of the hydrogen, and the mass of the nitrogen. Now I can turn those masses into moles. I noticed as I was working the problem that I used the incorrect information. Instead of 35 milligrams, there should have been 33.5 milligrams. The corrected values are in blue. So I'm going to take my 9.551 milligrams of carbon and turn it into moles. 1 millimole of carbon weighs 12.01 milligrams of carbon. 1 millimole of hydrogen is 1.01 millimoles of hydrogen. And 1 millimole of nitrogen is 14.01 milligrams of nitrogen. And when I turn all these guys into moles, I get 0.761 millimoles of carbon, 4.56 millimoles of hydrogen, and 1.52 millimoles of nitrogen. I'm going to divide everything by the smallest number of moles, in this case 0.761, and I get 1, 5.99 or 6, and 2. So the empirical formula for my substance is CH6N2. Now, the determination of the molecular formula from the empirical formula also requires one bit of information. We need to actually have the information of the molar mass of the compound. You can actually determine the molar mass of a compound without actually knowing its formula. And so to determine the molecular formula from the empirical formula, you take the molar mass and divide by the empirical formula mass. This should give you an integer that you can then multiply the subscripts of your empirical formula by to obtain your molecular formula. Again, this is best illustrated through a problem. In this problem, adipic acid is an organic compound composed of 49.31% carbon, 43.79% oxygen, and the rest hydrogen. If the molar mass of adipic acid is 146.1 grams per mole, what are the empirical and molecular formulas for adipic acid? This is a very common style of problem in which you are given the information to determine the empirical formula as well as the molecular formula. So again, we continue to do mass percent problems for empirical formula just like we did before. We're going to assume we have 100 grams of sample. Then what we get, instead of percentages, is we get masses. This becomes 49.31 grams of carbon, 43.79 grams of oxygen, and it says the rest is hydrogen. So if I subtract 100, these numbers from 100, I get 6.90 grams being hydrogen. I'm going to convert these into moles by using the molar mass. 1 mole of carbon is 12.01 grams of carbon. 1 mole of oxygen is 16.0 grams, 0 grams of oxygen. And 1 mole of hydrogen is 1.01 grams of hydrogen. And that's going to give me 4.106 moles of carbon, 2.737 moles of oxygen, and 6.27 moles of hydrogen. Dividing all of these by the smallest number of moles, 2.737 yields 1.5, 1, and 2.5. Notice I did go through and correct math error. Instead of 6.27 moles, it should have been 6.83. Now, these are not whole number ratios, so we need to multiply these by a number that will turn it into a whole number ratio. So I'm going to multiply everything by 2. So 1.5 times 2, this gives me 3. 1 times 2 is 2, and 2.5 times 2 is 5. So my formula, my empirical formula, is going to be C3H5O2. That's my empirical formula. To determine the molecular formula, I am going to take the empirical formula mass and divide it into the molecular mass, or the molar mass. So I'm going to determine the empirical formula mass much like I would any other. So I add up all the masses for all the elements in the empirical formula, and I get approximately 73 grams per mole. To determine the molecular formula, I'm then going to take the molar mass, given as 146.1 grams per mole, and divide by the empirical formula mass of 73. When I do that, I get an integer, 2. So this number then becomes a multiplier for the subscripts of the empirical formula. So my molecular formula now becomes C 3 times 2, H 5 times 2, O 2 times 2, or C6 H10 O4.